Hello and welcome. Today, we're diving deep into a topic that's frankly shaping the future of our electrical grids, and that's inverter technology. We're going to break down the two big philosophies here, grid following and grid forming, and really get into what they mean for a world that's leaning more and more on renewable energy. So let's jump right in. To really frame this whole conversation, let's start with a really important question. For about a century, these massive, spinning, synchronous generators in our old power plants have been the grid's pacemaker. They provided that steady rhythm, that stability it needs to work. But they're retiring. We're phasing them out. So we have to ask, what's going to replace that essential heartbeat? All right, here's our game plan. We'll kick things off with the big stability challenge we're all facing. Then we'll get to know the two key players, grid following and grid forming inverters. After that, we'll put them head to head, really compare them technically. And finally, we'll talk about what this all means for the future grid. Okay, first up, the grid's stability challenge. You see, with the old grid, stability wasn't really something we had to engineer separately. It was just there. It was a natural built-in property of those huge rotating machines that made our power. And that natural property has a name: inertia. Just think of it like the grid's shock absorber. So when there's a sudden jolt to the system, say a power plant unexpectedly trips offline, it's the sheer physical momentum of all those other spinning generators that resist the change in frequency. It buys the grid precious time to rebalance. Now this slide right here, this shows what happens when you don't have enough inertia. So an interconnector between England and France tripped, and suddenly the grid frequency in Great Britain started plummeting at a rate of negative 0.11 hertz per second. For engineers, that number, the rate of change of frequency, or ROCOF, is a huge deal. If it drops too fast, protection systems start kicking in, and you can get cascading failures. In other words, a massive blackout. So here's the bottom line. As we shut down these old coal and gas plants, we're not just losing power generation. We're losing the physical inertia and what we call system strength that they gave us for free. And that makes the grid weaker, it makes it more fragile, and it creates this big stability gap that modern technology absolutely has to fill. Which brings us to our first contender. This is the technology that honestly made the renewable boom of the last couple of decades possible. I'm talking about the grid-following inverter. So by definition, a grid-following, or GFL inverter, does exactly what the name says. It listens to the grid. It measures the voltage waveform that's already there, and then it injects a very precise amount of current, perfectly in sync with that signal. It is, at its core, a follower. And this quote from the Energy Systems Integration Group just nails it. During a disturbance, in that critical first fraction of a second, a GFL inverter is designed to act like a constant current source. It just tries to keep its own power output steady, and it counts on the rest of the grid to sort out the instability. So how does it actually do this? Well, the brain of a GFL inverter is its phase-locked loop, the PLL. This is the fancy circuit that locks onto the grid's voltage. But here's the catch. That PLL needs a clean, strong signal to follow. If the grid is weak, meaning the voltage is unstable and jumping around, the PLL can get confused, it can lose its lock, and that can cause the inverter itself to become unstable. I love this analogy because it's perfect. A GFL inverter is like one of those tagalong bikes for kids. Yeah, it's adding power, it's helping push the whole system forward, but it has zero ability to steer. It is completely dependent on the main bicycle. That's the strong, stable grid to set the direction and keep everything upright. Okay, so that brings us to the alternative grid-forming inverters. If GFLs are the followers, then GFMs are designed from the ground up to be leaders. They offer a totally new way to create stability in a grid that's full of renewables. The huge difference is right here in the definition. A grid-forming, or GFM, inverter doesn't need to listen to some external signal. It creates its own internal voltage reference. It gets to dictate the voltage and frequency. It can, in effect, form a stable grid all on its own. And here we go, here's the matching quote. In that same critical moment after a disturbance, a GFM inverter behaves like a voltage source. This is a game changer. It acts way more like a traditional synchronous generator, inherently working to hold the voltage steady instead of just its own current. So what does that let it do? Well, because it maintains its own internal voltage phasor, that's just a way to represent both the voltage magnitude and its angle, a GFM inverter can operate totally alone in what we call an electrical island. And most importantly, it provides what we call synthetic inertia.
By watching the grid and seeing that angle change during an event, it can instantaneously push or pull power to fight that change. It's mimicking physical inertia, but without any big spinning metal.
Okay, time for the main event. Let's put these two technologies right next to each other and really break down where they differ on the engineering stuff that actually matters for grid stability. This table gives us an awesome at-a-glance overview. You can see right away how GFM inverters line up so much better with what traditional synchronous machines could do. They're a voltage source, they provide synthetic inertia, they can operate in an island, and they can even kickstart the grid from a blackout, things a GFL inverter just can't do. Let's dig into that control philosophy for a second. GFL is a current source. It takes its orders from power commands and that PLL, and it injects current. GFM, on the other hand, is a voltage source. It sets its own voltage, and it just lets the laws of physics figure out how the current flows. It's a completely different, fundamental way of interacting with the network. And that difference becomes so critical during a disturbance. The GFL inverter, it's just trying to hold its current steady, but its PLL might get thrown off by a voltage sag or a phase jump, and it could actually make things worse. The GFM inverter, though, it's trying to hold its internal voltage steady, and that means it naturally, instantly changes its current output to support the grid, acting like a stabilizing force. This all leads to a massive advantage in weak grids. GFL inverters, they need a certain amount of system strength just to operate without going crazy. A GFM inverter doesn't. In fact, by acting as a strong voltage source, a GFM installation can actually increase the system strength in a weak area, which makes it possible for more standard GFL renewables to connect nearby. It's a true grid enabler. All right, let's head into our final section and see how all of this comes together in a blueprint for the future grid. We'll look at the very real challenges, but also the incredible opportunities of rolling this technology out at scale. I mean, the opportunities are huge. We can host way more renewables, we can replace those essential grid services, and we can build much more resilient systems that can restart themselves. But the challenges are just as real. We don't have clear standards yet, the controls are more complex, and to provide services like inertia, a GFM inverter needs to be hooked up to something that's always available, like a battery. And all of this creates a classic chicken and egg problem. You have the system operators and regulators who are still trying to figure out what they even need to ask for in their grid codes. But without those clear rules, the inverter manufacturers are, pretty hesitant to invest a ton of money into developing and standardizing commercial products. Breaking that cycle is really the key to unlocking GFM. Which leaves us with the ultimate design question for the grid of the future. See, it's not going to be about choosing one or the other. Instead, the real challenge for all of us power system engineers is figuring out the perfect mix. How many leaders do we need, and where do we need them to make sure we have a stable and reliable grid that's built on a foundation of followers? That is the puzzle we now have to solve.